The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
Hello and welcome back to Element 14 Presents. I'm Caleb, and in today's episode, we're going to build an Arduino-based unit conversion calculator.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
As makers, we're constantly looking up technical documents that have things measured in tenths, fractional, or metric. And if you're real lucky, they won't even mention the system of unit that they're using. The problem here for me is that there's no standard that people or companies are following. In one build, I will almost always find all three systems in use across various datasheets or technical drawings. I've personally standardized on metric, even though I am in the US and grew up using Freedom units. What that means is that I have a lot of conversions to do. I have a calculator that can do it, but it takes a lookup table and a bunch of extra button pushes to get the result. And by far the easiest way to do it is to fire up a Google tab and type the whole thing out. 5/16 to tenths. 0.3125 to millimeters, whatever. Sometimes Google can decipher your request and just give you the info, and other times you get 400,000 results to a conversion chart that was made in HTML 1.0 and migrated from a GeoCities website. Those solutions will work, and they've gotten me through the years, but I want buttons. I want something on my desk that I can just use without having to open an app on my phone or on my computer. First off, I want to mention that during the planning of this project, I got quite a bit of feedback from people saying that they wanted to build one as soon as I was done with it. I took that into consideration through the planning and design to make it as easy as possible to replicate. I'm using parts that are easy to work with, inexpensive, and readily available. I'm also going to write the software in a way to make it easy to add new conversions with just a software update. It's a pretty simple concept. There needs to be a keypad for input, a display to show you the result, and a rotary encoder for menus. I think we're going to need about 20 buttons, standard 10 key plus basic calculator functions, and a few extra keys like space and slash for fraction input. The idea is that you can rotate the rotary encoder to select the type of conversion and then just key in the value and hit equals to get the result. I would also like to build in a basic arithmetic calculator so there's just one calculator on my desk. Let's take a quick look at the parts and see what we're going to use and then get started with this. The microcontroller of choice for this project is going to be the good old classic Arduino Uno. They're cheap, easy to get, and there's just a ton of community support for them. Taking a little different route with the switches this time. Not the normal ITW switches, but Cherry MX. I've had them in stock and I just haven't used them in a project, and I thought this would be a great application. They're going to be super smooth and we can print our own keycaps for them. And these are specifically the Cherry MX Browns. And for navigating menus, we're going to use a rotary encoder. I really like these Bourne's rotary encoders. They're just a little bit nicer than the cheap ones that come on breakout boards. For the display, I chose a 20x4 LCD character display, partly because they're cheap and easy to get, and partly because I've used them so many times in the past. I know I can control the backlight, and they're going to work just fine with I2C. The case design was really fun to do with this project. It's pretty simple, but I took the time to do a few things that I usually don't, like hiding fasteners and paying attention to aesthetic. As usual, I load up all of the electronic parts and roughly place them where I think they should go, then start building around that. In this case, I needed a plate to hold the Cherry MX switches. I wanted it to be removable because this is the first time I'm doing a matrix and figured it would need to come out at some point. Since that needed something to mount to, it just kind of came together from there. I wanted to do a top and a bottom shell that would screw together from the bottom. The bottom shell worked out great for 3D printing as it could just sit flat and everything is mostly vertical on it. The top shell is kind of a strange shape and not that great for 3D printing, so I split it into two pieces and added a couple of key points so they would fit together. At first I built the keypad flat, then I angled the keypad by 5 degrees and it made a huge difference in how it looks. The rotary encoder, a couple of switches, and the display all mount to the top rear part. I left a cutout in the back for the Arduino USB port for powering the device as well as software updates. All right, let's print everything out and then put it all together.
Want to build the project in this episode? Want to download the code? Find the parts list? Want to ask a specific question and know this host will answer it? Simply take out your phone and point your camera at this QR code. This will take you right to all the details you need to get started. We'll see you on the Element 14 community.
All right, so got everything together, and then I immediately tore it back apart because when I turned it on, it wouldn't boot. And so I immediately figured that there was something wrong with the wiring and the display maybe, because what happens when you plug it in, powers up, and it should say something on the screen, and it does not. So what I did was I took it over to my computer over here, plugged it into the same workstation I've been writing the code on, and it fired up no problem at all. So I brought it back over here, plugged it back into the power supply. Same thing, doesn't work. Well, I've got a little Mac Mini right here, so I thought, well, let me try a different power supply. Just a regular USB port on a computer. Plug that in here. What do you know? It works. Unplug it from that, plug it back into the power. It doesn't work. I thought, what, does it need to be recognized as a USB device to turn on? I've never heard of that before. So I tried a different power supply. And look at that. It came on. Works. So let's take a look at these real quick. This is just a really cheap little adapter phone charger type thing. I think I bought like 10 for $5 at Fry's or something. And I have used these to power Arduinos, Raspberry Pis. Since I have a bunch of them, I use them all over the place, and they seemed to work. I tried it on both ports, the 2.1 amp and the 1 amp. Neither one of those work. So the one that I replaced is kind of even cheaper and chintzier than the other one, but it works. Try it one more time. There it is. But anyways, if anybody knows why one power adapter would not work on an Arduino Uno and another one would, please let me know. That would be super interesting to figure out what's going on here. Like I said, I've used this to power Arduinos before without a problem, but there's just something going on in this specific setup. So anyways, it's all together. I pulled it apart to troubleshoot it. I'm gonna put all the screws back in, and then we'll take a look at some code, get the keycaps on, and try it out. Let's have a look at the code real quick. We're just going to go over this briefly and show you how to add a new conversion type if that's something that you're interested in doing. The code will be on GitHub. There will be a link on the Element 14 community site to get to that GitHub page. Not much to do in the main script here, or the main program. Where you want to go first is over to display.h, and we have a couple of arrays here. One of them is the units. So you have, for example, metric and fractional. They have an index of 1 and 2. And down here is a unit matrix where you can see the metric to fractional is 1 and 2. And that refers to this up here. And that is assembled and referred to in the C++ file for this library. And then what happens when you want to flip it from metric to fractional to metric is when you click that button, it actually swaps these two bits here. So it's kind of semi-permanent until you reboot it. So if you normally do fractional to metric rather than metric to fractional, it will just stay that way once you click the button to flip it. That's the first thing that you have to do. And then you go over to unitconversion.h. You can name any function in here. It's probably going to be a void type function because of the way that data gets displayed. It's not returned, it's just displayed. Then you pop over here into unitconversion.cpp, and this main function here, convert, goes through the matrix index. So whatever thing you have selected, when you hit equals, it's gonna eventually get to here. Look to see which matrix ID is currently selected and then run the function associated with it. Over here, you would just add a new line with your stuff in it, and that would be index 11. Come over here, case 11, put your function name in there. And then the way that these functions work for the simpler ones is all the input is a character array in this input buffer. We convert that to a float so we can work with it, do whatever you do, your fancy math. And then we convert it back to a character array in this result. And that gets handled by display.cpp over here in this result buffer. It ends up that way. And that swap happens in the main program here, where it does its thing and then it does the copy from input buffer to unit input buffer and then display result buffer to unit result. And then it does the display draw. So that's it, brief overview of how to add a new conversion type. So if you're interested in that, that would be awesome, because we all get the updates if you want to do something, because all you have to do is compile it and upload it. So be sure to look for the link on the Element 14 community site. Now that the power thing's all sorted out, we can have a look at the unit and see how it functions. I'm pretty happy with the way that the case turned out. No visible fasteners, kind of a fun shape. The part of the case that I'm not super happy with are the keycaps. I had this grand idea of indenting the letters and numbers and everything into the cap, printing them, filling it in with some nail polish, sanding off the rest of it, and they would look awesome. But it didn't really turn out that way. As you can see, some of them are pretty funky. Tried some with paint, tried some with ink from different pens, and what ended up working the best for this was just a regular pen, and it still didn't turn out that great. In fact, if you build one of these, I suggest buying keycaps and just using those, unless you really want to print them and go through it. It just, in the end, probably wasn't worth the time for me, but I am happy that I did it. I can say that I have now. I also want to say that there are a couple of features that are not working yet. All the hardware is okay, it's just software. The first one is the basic calculator functionality. So just regular arithmetic calculator, punch in your number, your operator, number equals, and then you get a value back. I just ran out of time on that. It's probably a quarter of the way written. It's more complicated than I ever thought it would be, but I'll get back to it and finish that off. Or if somebody else wants to work on it, then be my guest. I'll be on GitHub. The other thing that didn't work are these two buttons. The buttons work, and that's just fine. And what the intent was is that by default, everything in metric is in millimeters on this. So if you wanted to convert your result from millimeters to centimeters to meters to kilometers, then you could do that by pressing up or down on those two buttons. Again, it's just software. Didn't get around to that part. I will eventually, because it's maybe not essential, but it's helpful, since the whole point of this thing is unit conversion. All the rest of the conversions work, except for this one. My math is just a little bit wrong on it, because what I didn't realize at first was that it takes angle into account in the calculation. I thought at first it would just be a direct correlation of lumens to candela, but it's not. There's an angle in there and another variable that you can or can't use sometimes. I don't know. I thought about just having it be a 360-degree angle all the time, and that's just static, but then I have to say that in here somewhere, and I don't have the functionality to have notes for each conversion type. But let's take a look at a few of them. all the rest of them work, which is great. But let's take a look at this one first. So tenths to metric, pretty straightforward. We'll do 0.25 equals 6.35 millimeters. 0.5 equals 12.7 millimeters. And if you want to do metric to tenths, you just push straight down on that and it will flip the units. So you could do 12.7 millimeters is half an inch in tenths. Now we can look at how the fractional stuff works. So metric to fractional. No, that's not what I want to do. 25.4. What do you think that's going to give me? Not 25.44, 25.4 equals 1. You can do strange numbers, and it'll give you a weird fraction because that's the best reduction that it can do. Turns out reducing fractions in software is hard, for me anyways, and it spent a lot of time trying to get that just right, and I don't know if I did it right. So if somebody else wants to have a look at the code and if you can fix that, that's awesome, but I think that's the best that it can reduce. Let's have a look at some more. Fractional to tenths, that's pretty cool. So you want to do like 12 inches and then you hit space, 3/4 3/4 equals 12.75 inches. You flip-flop that. $15.25, it's 15 1/4 inches. And we get to the one that doesn't work, and then we have some speeds. Look at those, whoops. Of course, you can flip-flop each one of these. And I put in inches per second and millimeters per second from miles per hour to kilometers, and then even millimeters per second to inches per second, because when I'm working in robotics, that's how everything is measured. Not looking at miles per hour, it's usually inches per second or millimeters per second. But I'm always curious how fast my robot's going. So if I have all of my calculations done in millimeters per second, and I want to know how fast my robot's going, I can do 2025 millimeters per second is 4.5298 miles per hour. Well, I'm glad it turned out the way that it did. All the hardware works, it's just software stuff now. And I hope that you guys will build one of these and be motivated to work on some of the code, because I'm not the best software developer, and my spaghetti code is sketchy.
Well, that's all we have for today. I ran into a couple of snags, but nothing that put an end to the project. The first thing was the power issue, and the second is the ever-elusive time. If you do end up building one of these, and I hope that you do, keep in mind that this is still in alpha prototype built only once state. There might be a few bugs in the design, and I'm sure there's more than a few bugs in the code. What conversions would you have added to this? And if you know what was going on with that power issue, let us know at the Element 14 community at element14.com/presents. We'll see you next time, and until then, keep making.